Good morning, students. Welcome in next lecture of Math of 242 Operation Research. So presently we are doing the numerical example on different queuing models. So in continuous of that, audibility is okay.
Yes, sir.
So here we have the question: ship arrive at a refinery at the rate of 5 per week. So ships are arriving. Ships means customer, and rate is given to you as a lambda. The refinery has one unloading berth with an average service rate 10 ships per week. So this is given to you as a mu. Assume Poisson arrival and exponential service, that is the M1 one berth. Now there is no statement about the discipline, so we have to assume FCFS infinity model. So in this, we have to compute what is the mean number of ships at the refinery. So mean number of the ships at the refinery means uh, in queue plus in service. That is, we have to compute the L. What is the mean time spent by the ship at the refinery? That is the W. So this is the MM1 model, and you have to compute the L and W. So we know that L is what? Lambda upon mu minus lambda, and W is 1 upon mu minus lambda. So both you have. So here we have the L is equal to rho upon 1 minus rho, or lambda upon mu minus lambda, that is 1, and W is equal to L upon lambda, or 1 minus mu minus lambda. Any formula you can use. So it is the 1 by 5 week. So this is the question of MM1 queuing model. In continuous of that, the company has second unloading berth. The company has the second unloading berth with weekly rent of 7,000. Means if you are using the second berth for unloading, so company has to pay 7,000 per week. The service time of this berth is also exponential with mean rate as its own berth, means both has the same service rate, that is mu is equal to 10, namely 10 ships per week. For the lost week of the ship at refinery, the company losses the 18,000. If company is not able to unload the ship, then the company has to face a loss of the 18,000. So what will be the average number of the ships at the refinery after the new arrangement? Means we have to compute the L. So main thing is the ships are arriving following the Poisson process M, providing the unloading with the exponential service time, right, or exponential distributed unloading time, that is the M. Now we have the one one own worth, or means one own unloading worth, plus one in higher, one with higher. So here we have the S is equal to 2. Then we have the FCFS infinity and infinity. Now this is the model of multi-server. So for the multi-server, we have to compute the L and W here. What will be the average time spent by the ship at the refinery? So we know that what is the P naught. P naught, first we have to compute the P naught. P naught is 1 plus rho plus 2 upon 2 minus rho, when we have the S is equal to 2. When we have S is equal to 2, so we have the 1 plus rho plus 2 upon 2 minus rho. And rho, we have the rho. What is the rho? Rho is equal to lambda upon mu, and lambda is 5 upon 10. That is the 1 by 2. So on putting the value of rho, we have the P naught as, we have P naught as it's rho square. It's rho square. Rho square upon 2 minus rho. So it will be the 3 upon 5. So having the knowledge of the 3 upon 5 or P naught, we can compute the LQ. LQ is what? Rho to power s upon factorial s, rho upon s 1 minus rho upon s whole square into P naught. So rho is equal to half, s is equal to 2. So here you have the value of LQ as 1 upon 30. From the value of the LQ, we can compute the L using the formula L is equal to LQ plus rho. Means in the sequence only you can determine, directly you cannot not apply the formula. So first you have to come in the multi-server model. When we have the multi-server infinite capacity, infinite population model, we have to compute first what is the P naught, then LQ, then only you can compute the L. So L is equal to LQ plus rho. So it is coming the 16 by 30. So you can see here the 16 upon 30, and here we have the it is 1. So if you compare naturally, the expected number of ships in the refinery will reduce because we are increasing the service facility. So it is reducing from 1 to 16 upon, right? It is reducing from 1 to 16 upon 30, right? So naturally, when you add the service facility, the expected number of customer in the system will reduce. Then average time spent by the ship in the refinery will be the W is equal to L upon lambda. So W you have already computed. So here it is the 16 by 150. So this also you can observe. Here the expected waiting time is 1 upon 5 week, and there it is coming 16 upon 150 week. So you can see, as you increase the service facility, whether on rent or whatever the way, right, you are purchasing on rent and whatever the way, as you are increasing the service facility, the expected number of customer in the system and expected waiting time of the customer in the system reduces. So here now in this case, one information also given to you, that the company has second unloading berth with weekly rent of 7,000, and the service time for this berth is also exponential with the same rate. And for each lost week, of the ship at the refinery, the company losses the 18,000. So it means, what will be the total cost? What will be the total cost? Total cost will be the rent plus losses, rent plus loss. So loss is given to you 18,000. Loss is given to you 18,000, and rent is the 7,000 for one additional unloading berth. And this 18,000 is given to you per week per ship. So it is the 18,000 into n. 18,000 into n. So if you compute the expected total cost, so this will become 7,000 plus 18,000 into L. So now they are asking whether the new arrangement is profitable or not. When S is equal to 1, then what is the total cost? Expected total cost. When S is equal to 2, then what will be the expected total cost? Means expected total cost when we have expected total cost for S is equal to 1. For S is equal to 1, it will become 18,000 L because there is no rent. But expected total cost when S is equal to 2. So at that time it will become 18,000 L plus 7,000 plus 7,000. Clear? So now we have to check which arrangement is better. So here we have the cost when S is equal to 2. Total cost per week in the new arrangement. New arrangement means when S is equal to 2. So it is coming 16,600. And for the old arrangement, for the old arrangement, it is the 18,000. So it is coming 18,000. So naturally, new arrangement is profitable for the company. Clear? So this type of the numerical example we can ask from the different queuing model. Is there any doubt? Anything you want to ask? Now, let us have this problem. Truck arrives at the service station in Poisa process at mean rate of 10 per hour. So, what is given to you? Here we have the lambda, and it is following the Poisa process. The service station has two server in parallel. Two server in parallel. That implies S is equal to 2. Each with mean service rate 10 trucks per hour. 10 trucks per hour. That is the mu. Mu. Service times are exponential. So when the service time is exponential, it means this is the example of MM2. MM2, there is space for only two trucks being served and for two in waiting. It means we have the limited space. So when we have the limited space, it means what is given to you? Anyone, please? What is given to you? Yes, please try. Here we have the limited capacity, right? Here we have the limited capacity. So it is the FCFS and M is equal to 2 plus 2. 2 in service, 2 in queue. So total system capacity will become 4. If all spaces are filled up, the truck will go another service station. That is the lost truck. That is the lost truck. So this is the example of FCFS. Right here we have the S is equal to 2, so multi-server, M is equal to 4. So it is the example of multi-server finite capacity queuing model. And here we take the population size as infinity. So this is the example of MMS, FCFS, M infinity. Now, so when we have such type of the question, instead of applying the formula, whatever the formula I have derived, instead of applying the formula, just use the worth and process. So here, so first we compute the state probability of such problem. So in this case, what I am saying that always use the worth and death process. Means here we have the 0 truck, 1 truck, 2 truck, right, and 3 trucks and the 4 trucks. They are arriving with the rate lambda is equal to 10, lambda is equal to 10, lambda is equal to 10, lambda is equal to 10. Means if the problem is of finite capacity and finite population and this finite is less, then always prefer the birth and death process. If this m or k is more greater quantity, then you apply the formula. And here the mu is equal to 10. Here we have the mu is equal to 10. Here you have mu is equal to 10. And here you have the mu is equal to 10. So in this case, we have the C naught is equal to 10 upon 10, right? Lambda upon mu, that is the 1. C1 is C1 is equal to this. C2 is equal to also 1. Okay, 1 minute. Here we have the 2 mu. 2 mu means it is 2 mu. 2 mu, that is the into 20, 2 mu, because we have the multi-server model. So here we have the C1 is equal to 1, C2 is equal to 10 upon 10 into 10 upon 20, that is the 1 by 2, and C3 is equal to 10 upon 10 into 10 upon 20 into 10 upon 20, that is the 1 by 4, and C4 is equal to 10 upon 10, right, 10 upon 20, 10 upon 20 and 10 upon 20, that is the 1 by 8. So P naught is what? P naught is 1 plus C1 plus C2 plus C3 plus C4 inverse. So that is the 1 plus 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 inverse. So here we have the, right, so here we have the P naught as P naught we will get as a 8 upon 23. P naught will be the 8 upon 23. Clear? Now from here, whatever we have to compute, that we can compute now. So when the P naught is 8 upon 23, so P1 will be also 8 upon 23, because C1 into P naught, it is the C1 into P naught, and P2 is equal to C2 into P naught, that is the 1 by 2, so 4 upon 23. P3 is equal to C3 into P naught, that is 1 by 4, so 2 upon 23, and P4 C4 into P naught, so it is 1 by 23. 1 by 23. So here you have computed the all the state probabilities, and always prefer to write the Pn is equal to 0 and greater than equal to 5, because when we ask the state probability, so you have to write the all the state probabilities. So it is mandatory to write here Pn is equal to 0 for n greater than equal to 5. So here we have computed the all the state probabilities. Now after having the knowledge of the state probabilities, here we have to compute what is the expected number of the truck in the system, that is the L. So L is what? Here L is NPN, so 1P1 plus 2P2 plus 3P3 plus 4P4, and all the values you have, so just you put the value of the P1, P2, P3, P4. So here the L will come 26 by 23. 26 by 23. Then after we have to compute the fraction of the customer lost, means the fraction or the proportion of the customer lost. So that we have to compute the P4, that is equal to PM, right? Fraction of or proportion of customer lost is equal to P4 or PM. So P4 we have already computed as 1 upon 23. So here we have the 1 upon 23. So it is given to you here P4 is equal to 1 upon 23. Then after, what is the per hour effective rate of service? Effective rate of service for the service station. So effective rate, that is the mu bar. Effective service rate, that is the mu bar, and we know that for the for the steady state it is equal to lambda bar, and for the for MMSM system we have computed this is equal to lambda into 1 minus PM. So that is lambda 1 minus P4. Lambda is 10, P4 is 1 by 23. So here we have the required value, right? 1 minus P4 into lambda. So here we have the required value, 9.57. So you can notice here this is less than 10. It means 0.43 are the lost customer, right? They are the 0.43 proportion is the lost proportion or lost truck. Lost truck. Clear? Then after, what is the proportion of the idle time per server? Idle time per server. So first we compute the expected idle time. So here we have the two both servers are idle when there is no truck. One server is idle when there is only one truck, and you have to compute the per server, so divide by 2 because we have the two servers. So we have to compute the 2 P naught plus 1 P1 or divide by 2. So that will give you, so first we compute the expected idle time, then divide by 2. So that will give you idle time per server. So here we have the proportion of the idle time or expected idle time 2 P naught plus P1, that is the 24 by 24 by 23, and per server, due to the per server we divide by the 2. So it will come 12 by 23.
Sir,
Yes.
sir, why do we divide by 2 over here?
Per server, because we are talking, we have the two servers, no?
Okay, okay, right. Yes, sir.
We are computing per server. It is written here, no? Per server.
Yes, sir, got it.
Now answer all four questions above if we have the three space provided for waiting. So in that case it will become mm to FCFS m is equal to 2 plus 3. 2 in service plus 3 in waiting and infinity. So that is the m is equal to 5. So you have to repeat all complete question, right? By considering the m is equal to 5. So I am not repeating, you can do yourself. So here again you have to go with the birth and death process. So when we go for the birth and death process, so here we have to make one more node, that is the for the 5, and here we have the lambda is equal to 10, and mu is equal to 20. Mu is equal to 20. So in that case, the C5 will come. C5 will come 1 by 16. 1 by 16. So P naught, in that case, the P naught will be the 1 plus C1 plus C2 plus C3 plus C4 plus C5, and here we have the inverse. So P naught will come 1 plus 1 by 2 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16 inverse. So the P naught for the second arrangement, right? P naught for the part B will come as a 16 upon 47. So from here we can compute the value of P1, P2, P3, P4 and P5 as 16 by 47, 8 by 47, 4 by 47, 2 by 47 and 1 by 47. So after the having the knowledge of all the state probabilities, we can compute now the all these four subparts. Now main thing is this question number C. If the provision of the third waiting space cost rent of rupees 5 per hour, that is the rent, and the revenue from the service of truck we have the rupees 10, will the provision of the third waiting space be profitable? Means we have to compute the profit. Profit is what? Revenue revenue minus rent. Revenue minus rent, right? Revenue minus rent. So rent you have to rent you have to provide at with the rate 5 per hour, and revenue you are getting the rupees 10. So revenue you are getting from the service truck, right? Service truck. So here it will be the here per hour revenue will be the per hour revenue will be the 10 into mu bar, 10 into mu bar. And how much the rent per hour you have to give? That is the rupees 5. That is the rupees 5. But you know that effective service rate for the steady state is equal to lambda bar. So it is the 10 lambda bar minus 5. So you have to compare the expected profit with m is equal to 4 and m is equal to 5. So these are the that four parts when m is equal to 5. So you can compute yourself all the, just we have to compute the L, right? P5, then lambda bar is, because this value we required, so lambda bar is 460 upon 47. Then after proportion of the idle time, that is the 2 p naught plus p1, then divide by 2, so per server it will come. So here we have the per server. Now the extra truck serviced per hour providing the extra waiting space. So in this case, what is the extra truck serviced? Means mu var when we have m is equal to 4 and mu var when we have m is equal to 5. So it is equal to lambda for lambda for 4 minus lambda var for 5. So it is the 9.7. So here you can see this is the 9.79, and here we have this is the 9.57. So here we compute the so it will be the we have to reverse this lambda 5 lambda 4. So here we have the 9.79 minus 9.57, that is the extra service truck per hour, extra service truck per hour. And from this extra serviced truck, you are getting the additional revenue as 2.2 with the rate 10 per hour, right? With the rate 10 per hour, you are getting the rupees 2.2, and 5 rupees you have to pay as a rent. 5 rupees you have to pay as a rent. So naturally you can see the revenue you are getting the 2.2 only, but you have to spend 5 rupees. So it implies that new arrangement is not beneficial. Taking the space on rent is not beneficial, is not profitable. Clear? What is the gist of the question?
Sir, how did we calculate extra revenue per hour from that new
Actually,
bar?
means here we nine means here that we have number of the trucks serviced,
Yes,
number
sir,
of the
that
trucks
point two two
serviced.
extra.
It is the 0.22, na difference is the
Yes, sir.
0.22 into
Yes, sir.
10.
Why? Why, sir?
Pardon?
Why do we do that?
Actually, it is given to you, na the each service truck, each service truck will give you the extra 10 rupees
Okay, okay. All right. Yes, sir. Okay, sir. Got
revenue
it. Got it.
revenue from.
Yes, sir. Yes, sir. Got it. Thank you.
So here we have the question number 17 from your book. At a service station, customer arrive in Paisa process. So customer arriving in the Paisa process, that is the M, at an average rate of 20 customer, lambda is equal to 20 per hour. There are two servers, S is equal to 2. There are two servers working in parallel. Time taken by each server to serve a customer is exponentially distributed, that is the M, with mean 7.5 minute. So 1 upon mu is given to you 7.5 minutes. That is, for each server the service rate will be 8 customer per hour. So this implies that mu is equal to 8 customers per hour. If the number of the customers at the service station is 5, an arriving customer is not allowed. If number of customers is 5, so that is the M, then no further customers are allowed, that is the lost customer. So lost customer, so here you can say this is the MM2 FCFS M is equal to 5 infinity model. Find the state probabilities. So first we have to compute the state probability. So I have told you, right? I have told you that always when we have the finite model, right? MM2 FCFS M infinity, when we have the finite model, always prefer to compute the state probability, right? Always prefer the birth and death process. So in this case, we have the 0 customer, 1 customer, 2 customer, 3 customer, 4 customers, and 5 customers. Arrival, here the arrival is with the rate arrival rate is given to you as a lambda is equal to 20. Lambda is equal to 20. So here we have the lambda is equal to 20, 20, 20, 20, and here we have the 20. Now we have the two servers. So when we have the one customer, it provides the service with the rate 8 only. When two customers, both server will be active, provide the service with the rate 2 into mu, right? That is the 16. That is the 16. That is your 16. So here C1 will come 20 upon 8. C2 will come 20 into 20 upon 8 into 16. And C3 will be 20 into 20 into 20 upon 8 into 16 into 16. And C4 will be 20 into 20 into 20 into 20 upon 8 into 16 into 16 into 16. And C5 20 into 20 into 20 into 20 into 20 upon 8 into 16 into 16 into 16 into 16. So from here we have the value of the C1, C2, C3, C4, C5. So P naught is what? 1 plus C1 plus C2 plus C3 plus C4 plus C5 inverse. So from here you have the value of the P naught, and P naught will come 512 upon 11017, right? That is the value of the P naught. Always prefer to keep this probability in the fraction. Never please write in the decimal. So from here the P1, P2, P3, P4 and P5 you can compute as Cn into P naught. All the Pn you can compute, and here it's good practice if you write that Pn is equal to 0 for n greater than equal to 6, so that we can understand we have computed all the state probabilities. Now in the B part, what proportion of the customer lost? Customer lost means whatever the capacity that we compute here, the PM, that is the P5. Here we compute the P5. Find the effective arrival rate of the at the service station, that is the lambda bar. Lambda bar is what? Lambda into 1 minus PM. 1 minus PM. Find the mean number of the customer served. Mean number of the served. So that is the mu bar, and mu bar is equal to lambda bar. Mu bar is equal to lambda bar, and lambda bar is what? Lambda into 1 minus PM. So here you can see. So the value of the mean number of effective arrival rate, it is given to you lambda into 1 minus P5, and it is coming 14.33, which is less than 20. So whatever the difference, that is the lost customer. Actually this much customers are joining, rest are the lost customer. They are eager to take the service, they are the prospective customer, but not able to take the service due to the limited betting space, system capacity. In the D part we have to compute the mu bar, right? That is the expected number of the customers served per hour. So for the steady state it is equal to lambda bar. Then after in the E part we have to compute, find L, LQ, W and WQ. So we know that what is the LQ? LQ is n minus S into Pn. So it will become n minus s, right, into Pn. So 2 minus 2, that will be, and summation start from, it is the summation n is equal to s to infinity n minus s into Pn. So instead of the infinity, we take the m. M is what? It is the 5, and s is equal to 2. So 2 minus 2, when we take, it is the 0. So it will be the P3 plus 1 P3 plus 2 P4 plus 3 P5. 3 P5, and all the value you have, right? P3, P4, P5, you have the value. So that will be the expected number of customers in the queue. From here, using the little formula, you can compute the expected waiting time as LQ upon lambda bar. So lambda bar already you have computed as lambda into 1 minus P5. So that is coming the 0.11 hour or 6.65 minute. Using the another little formula, we can compute the L in terms of the LQ as LQ plus lambda bar upon mu. Lambda bar upon mu. So LQ already you have computed, lambda bar already you have computed, and mu is equal to 8 is given to you. So when we put here, you have the number of customer in the system as 3.28. And using the little formula, we can compute W as L upon lambda bar or WQ plus 1 upon mu. So that is the expected waiting time in the system. Then after, in in part F, on completion the service, customer pays rupees 30 irrespective of the time devoted for service hour. Means the served customer will pay rupees 30. So total revenue will come 30 into mu bar. 30 into mu bar. And the cost to the service station due to presence of the customer in the system is rupees 15 per hour per customer. If there are n customers, customer cost will be the 15. So if you take the expectation, that will become the 15L. If you take the expectation of this, so 15 into En, and En is what? That is the L. So total per hour cost will be the this. Server is paid rupees 50 per hour. Server is paid rupees 50 per hour, whether that's busy or idle. Find the expected profit. So expected profit will be the revenue minus expenditure. Revenue minus expenditure, right? Expenditure. Revenue minus expenditure. So it will become 30 mu bar minus expenditure is what? 15L plus 50 into S. They are the two server. So you have to pay 100 rupees. Find the expected profit per hour to the service station. So that is the way to compute the profit. So it will become 30, right? Because for the steady state, mu bar is equal to lambda bar. Always we have to write the formula in terms of the lambda bar instead of the mu bar. When I'm writing here 30 mu bar, so next line you use the 30 lambda bar. So here 30 mu bar minus 15 L minus 50 S. So that is the expected profit is the 280.70. Let us have this question. In the parking lot, there are 4 parking space only. Car arrive in a paisa process. 4 parking space, that is the M is equal to 4. Car arrives in a Poisson process, that is the M, with a mean rate 10 cars, 10 cars per hour. The parking time of a car is exponentially distributed with mean 12 minutes. So 1 upon mu is equal to 12 minutes. So mu is equal to 5 cars per hour. 5 cars per hour. When all the 4 spaces are occupied, the arriving car goes elsewhere. Goes elsewhere, that is the lost customer. Lost customer for the parking. What is the probability that car that arrive at the lot have to be sent back because there is no parking space? Means we have to compute the fraction of lost customer. Fraction of lost customer means we have to compute the P4, or you can say PM. So we have to compute the P4. So for the this is the finite capacity model, and it is of mm, right? Mm. Now self, it is a little kind of the self service also, because we have the four service space, four service space or four parking space. So mm4 fcfs m is equal to 4 infinity. So this is the mixture of finite capacity and the finite or self-service model. So here we have zero car, one car, two cars, three cars, and four cars. Car are arriving with the rate. The cars are arriving with the rate here lambda is equal to 10. So it we have the 10. Here we have the 10. Here we have the 10. Here we have the 10. Now if there is one car, so service rate is 5, two cars, so 10, three cars, so 15, four cars, then it is the 20. Means mu, 2 mu, 3 mu, 4 mu. So this is the self-service model. So from here, C1 will be the 10 upon 5, C2 will be the 10 into 10 upon 5 into 10, and C3 is equal to 10 into 10 into 10 upon 5 into 10 into 15, and C4 is equal to 10 into 10 into 10 into 10 upon 5 into 10 into 15 into 20. So in this way, we can compute the C1, C2, C3, C4. Then P naught will be the 1 plus C1 plus C2 plus C3 plus C4 inverse. So when we have this, so you have the required value and you have to compute the P4. So C4 into P naught. That's the methodology we have to opt. So here we have the value of the P naught as 1 by 7, and P4 will come C4 into P naught, that is the 2 upon 21. So that much car will be the lost customer, lost car. So rest question we will do in next class. So probably on Monday at the 5 o'clock we can have the first announced quiz.
So, next week, sir.
Next week on Monday.
Okay, sir. Yeah.
I will notify.
Yes, sir. Thank you. Thank you.
Yes.